All right, thanks everybody. Yeah, let's get started here. Good afternoon. My name is David Moore. Very happy to be here. First, I want to say thank you to the volunteers and the staff and participants and everybody. When I submitted my proposal for this talk, I was unaware that it was the first ever BSides San Diego, so especially appreciative to be a part of this. Looking forward to many more. Real quickly, just a few details about my background. Been a software developer, professional software engineer since 1994. Had the opportunity to work for some pretty cool companies. I worked in engineering, sales, consulting, and business development roles. One of the highlights of my career came pretty early. I got a chance to work at Next, and before it was bought out by Apple, and was a fanboy of Steve Jobs since I was 14 or so. So that was a pretty extraordinary experience. And I was, for a few months, one manager away from Steve. My manager was the director of Web Objects Consulting. Web Objects was their web framework that they had at the time. And he reported to the VP of Professional Services. My direct manager left. So for a few months, I was one manager away from Steve. But that went okay. I was a consultant, I was a field consultant, and I was making a lot of money, so no problems there. Got to work for some other pretty cool companies as well. We got bought by Apple, and that was one of the most shocking emails I've ever gotten. You're now an Apple employee, and didn't see that coming. And ironically, I was done with Objective-C though. I was coding Objective-C. That was a language we were using for web objects, and I was like, Objective-C is going nowhere. Yeah, I just have to go to Java. And for my career's sake, and so ironically now Objective-C, of course, is in every device. And so that's cool. So and I worked for some other really great companies too. But then I kind of decided to move away from full-time employment and went into consulting. And that's me consulting in Indonesia.
Nice.
And so I was fortunate enough to do that. And then I had the opportunity to move into opera. I trained into opera for a couple of years, and then I was able to actually have a short career as a semi-professional Mozart tenor. I kind of took that as far as it would go, though. I actually got kicked out of opera for not being loud enough. And really at the same time, I wanted to get back into tech, too. I was really interested in it. I saw some pretty amazing breaches and hacks that were going on earlier in this decade, especially even starting back with Stuxnet. I was completely blown away by that. And then there have been some, very high-profile breaches. So I decided to go back into tech and just completely focus 100% on security. And to do that, I decided to just train myself. I worked with vulnerable web apps, lots of reading, lots of trying stuff. And then I went into bug bounty programs and found these very, very useful. Companies like BugCrowd, Cobalt, and HackerOne are intermediaries between researchers and companies, so that you can report a vuln and not be sued or interrogated. Instead, you might get some money, and you definitely get public recognition, which is really nice. And so I got a few of those. Full disclosure, the Google was not Google themselves. It's very hard. I actually got a couple of different Google acquisitions. So I enjoyed that, but then really wanted to go into something that wasn't so impacted. There's so many people doing web attacks. So often you report a vuln and you get duplicated. Somebody else already reported it, and you get nothing for that. And I was always interested in fuzzing or C, memory corruption. I've been working in C for a very long time. So pivoted into that, started fuzzing with AFL, American Fuzzy Lope. And then I got so into fuzzing that I decided to start a company called Fuzz Station, and we do fuzz testing at scale in the cloud. Okay, so today we're going to talk about how you go from having a bunch of crashes to getting a point where you have a good chance of either determining exploitability, being in a position to report that crash, or if you have to fix the crash, understanding where the root cause of the crash is. And so we're going to go over quickly memory corruption bugs. Not everybody's working in C every day, so I'm going to review that. Go through the workflow that I've developed during my research to approach these things. And then finally wrap it up with a couple of examples that I found in my research. And so first of all, we're just doing a quick review, the kinds of memory corruption bugs we see. What do we mean by memory corruption fundamentally? It's really invalid reads and writes. One way or the other, a program is coerced into reading or writing outside the bounds where it's supposed to. These are also called out-of-bound reads and writes, or OOB reads and writes you'll see often as well. And fundamentally, that's what memory corruption is, one way or the other. There's lots of different kinds, but it's one way or the other. It's reading or writing outside the bounds where you're supposed to. There's a variety of different causes of these. Off-by-one errors are extremely common. I see off-by-one errors really being the fundamental cause of these bugs in probably about 2/3 of the vulnerabilities I find. Unvalidated input as well, and stack overflows too, even stack overflows. And so yeah, there's two places in a process that store memory, the stack and the heap, two areas where memory corruption can take place. And the stack is where if you just declare a variable within a function, local, that's going to go on the stack. Any memory that's alloc goes into the heap, such as a buffer or an object. If you're calling malloc to create an object, that's going to live in the heap. Those must be explicitly freed by the programmer as well. Any memory that you alloc must be also freed by hand. And we'll look at a little more of that in a second. Heap and stack buffer overflows are common. And so we do still see quite a few of these. One quick note, you'll hear sometimes people just talk about a stack overflow. Sometimes the words aren't used in particularly carefully, but a stack overflow is when you have out of control recursion. If you're just recursing and it keeps going and you blow out the stack, that's a stack overflow. Today we're talking about stack buffer overflows where you're overwriting memory. And so here's just a quick example of a stack overflow. If you have a program that takes input from the command line, allocate buffer, string buffer, character buffer, and then you use a known bad function, stir copy, definitely known to be an unsafe function. Stir and copy is what we should be using now. And then if you drop in from the argument, copy it into this buff, you can easily overflow. So here we're sending 12 capital A's as an argument on the command line. And so that's going to overflow the stack by 4 bytes. Another very common and now sought out vulnerability is a use after free. And this is a heap vulnerability. And it's like it sounds, it's when a program continues to use a free pointer. So as we said, when you malloc memory, you get a pointer, you need to free it. If you free it and then use it again, that's a UAF, just like it sounds like. These have a very good likelihood of exploitability still. There's not many mitigations against these. And there are quite a few out there. So UAFs are probably the most sought after heap vulnerability that we're looking for at this point in time. These show up often during error handling. You can get confused. If there's an error, you're handling an exception, you're doing stuff there. Maybe you're freeing it and it's already been freed, or maybe you free it there and it gets freed again later. Or just in general, where it's unclear what part of the program is responsible for freeing memory. If it's not planned out very carefully, it's very easy to do this, to use memory after it's been freed. And here's a quick example, a pseudocode. We have a pointer, 4 bytes, get malloc to this pointer X. We do some stuff with it, whatever, a bunch of code happens. Then we free it like we're supposed to explicitly. But then maybe some more stuff happens and we wind up printing it. That's a UAF. Perhaps it's during error handling, or maybe we want to log that and we forgot we already freed it. So that's a classic trivial example of a UAF program, or UAF vuln. And there's a few other kinds of memory bugs to talk about. A double free or an invalid free is, you can think of it maybe the opposite, or it's related to UAF, but here you're freeing things twice. You're freeing something that's already been freed. And that's hard to exploit, but it can be, especially under race conditions in a multi-threaded system. Another very common memory bug is when a conditional depends on uninitialized memory. So if you say int x, but you don't initialize it, and then maybe you say if x, do something, that's at least undefined behavior and potentially hard to exploit, but could be exploited as well. And then one other memory bug that we're all definitely familiar with is memory leaks. And this is when you don't call free at all. You just keep alloc and it never gets freed. And this is not really exploitable in an overflow sense or to get control of a program, but it could be used as a bad guy deliberately to cause a DOS situation and continually and repeatedly do something that malloc space to the point where the memory is exhausted and the process calls to a halt. Okay, so we've been talking about exploitability a little bit. I'll be using the word, what do we mean? What really is exploitability? And one way to think about it is that it's reprogramming an application with input data and not code. If we can trick a program into executing attacker-controlled input data as if it were code, that's a code injection exploit. Another way to think about it is that input streams become instruction streams. That's an idea from Halvar Flake, pretty famous programmer. His real name is Thomas Dullian, and he just started at Google Project Zero, their own white hat organization. He started there in November. Very interesting idea. And in terms of in this kind of attack, it's about controlling the instruction pointer. If a bad guy can get control of the instruction pointer, and by that I mean EIP in 32-bit systems and RIP in 64-bit, they can jump to places and execute code. Now, in this case, we're talking about a code injection attack when they can supply their own code, typically in the form of shellcode. That's getting harder and harder to do for a lot of reasons. And so now we see more and more reprogramming the application with existing code that's already in the process. So because we can't get our own attacker-controlled execution code in there, instead we leverage code that's already existing. And it could be code in the application itself. More commonly, it's going to be code in a library that's been loaded. Any given application loads quite a bit of libraries, and the idea is there's a lot of code out there to use. And this is also called return-oriented programming, or ROP. And the idea is you chain together lots of little bits of code to get what you want, typically popping a shell. This also has an interesting name. Once things get to this point and you're able to reprogram a system at will, it's called weird machine programming. That's technically a term. You call it weird machine. Okay, so that's kind of what exploitability is from my perspective. Doesn't matter. Like, why do we care if something is exploitable or not? There's a few reasons. First of all, I would say, in a way, no. I mean, you have to fix memory corruption bugs. They should be fixed. You don't want anything crashing even under the most unlikely of input. And you don't want it getting exhausted out of memory or anything else. Any memory corruption bug should be fixed. However, there's lots of cases, or a couple, where it does matter. Certainly, if you are reporting the bug to vendors or maintainers of an open source software project, you need to motivate them and make it clear why it's an important bug, why it needs to be fixed. They have a backlog, so you want to be able to tell them, hey, this is highly likely to be exploitable, and here's why. Almost even more importantly, from the view of the researcher, you're kind of walking a fine line, because if you have a bug, typically you either file it with an open source project as a security bug explicitly, and that's private, or you just file it on their standard bug tracking program. And you have to kind of be careful if you call something exploitable, and a lot of times you kind of get a little knee-jerk reaction that it's not, and sometimes they're right, but you don't want to be seen as over-aggrandizing or reporting stuff as security when it's not. You know, boy or pride wolf kind of thing. You want to avoid that, but even more, the other side of the coin is that if it is exploitable and you report it as a normal bug and it goes right into the bug tracking system, which is public in a lot of cases, you potentially just drop the 0 day. So you really don't want to do that either. And so you walk a fine line, and the idea is, so that's really important to understand really how exploitable potentially what you're reporting is. Then finally, for developers, in general, if you're breaking your own stuff, the developers themselves might have a big backlog of bugs, so they would like to know what's exploitable. We need to fix that first. The next question is exploitable by whom? There's a broad range of exploit development skill. There could be, I mentioned Project Zero a second ago. This is Google's internal group. They're a white hat group. They check any software that a Google customer might use. Their purview is to look for bugs in it, and they have some very top people. I think they generally have about 12 to 14 people in Google Project Zero, and they have quite a few resources behind them being part of Google. Then you have this group. They also have quite a few exploit devs that are very good and amazing, and really extraordinary resources behind them. And then there's who knows who, whoever else is out there, nation states, other highly motivated groups, even individuals can come up with pretty amazing exploits sometimes, in some cases. So just to reiterate, we probably already know security is never 100%. We are trying to raise the cost of the attack to the attacker. We're trying to raise it higher than the value of the data or whatever motivation they have for making the attack. Another point is that most modern exploits, especially that you're seeing in browsers and things like that nowadays, it's rarely just one bug. It's getting rare and rare that one bug will really lead you to a full exploit, a full remote command execution. And so most of these exploits are few bugs. They're a couple bugs, 3 or 4 bugs chained together very carefully in a way that will reach you to that goal of fully exploiting the system. So it becomes somewhat moot to argue or consider whether or not a single bug is exploitable or not, when in many cases it could play a critical role in a bug chain, even though it in and of itself is not exploitable. And then we have some bugs that are pretty surprisingly exploitable, so it pays to keep an open mind. Specific example that was recently disclosed in Chrome OS, there is a library called C-Areas, and it is a DNS resolution library. And they had a 1-byte overflow, probably found with a fuzzer, and you could write past. It was a heap-based vulnerability, and you got 1 byte write overflow. So you could write 1 byte. However, that byte was always just the digit 1. The attacker could not control it, could not put their own data in it. And so it does seem unlikely that this would be exploitable or be very hard at first. It was considered by the Red Hat security team to be a moderate security impact, which is pretty reasonable, I think. But someone, and they are anonymous, found a way to get a full RCE, full root control exploit via JavaScript, actually, on Chrome OS with this vulnerability. So the way this kind of thing would happen is called heap grooming, and you have to make lots and lots and lots of calls ahead of time with the goal of putting the heap in an exploitable state. Now, this bug report was 37 pages. I've not read it. But the idea here is that you really can see, it's really hard to tell really what ultimately is going to wind up to be exploitable. And this is actually what triggered the vulnerability. If you simply add a trailing escape dot after the domain name, that would trigger this. So this is definitely the kind of thing, when you see this, it's pretty likely a fuzzer found this. Okay, so just to round out talking about memory corruptions in general, talk about some of the mitigations that have happened that make exploitation harder. Most of these have come out in the last 10 years or so. And stack canary is the first one to talk about. These are also sometimes called stack cookies. These are a random integer that's pushed in between stack frames. And it's just like a canary in a coal mine. If something's wrong with this stack canary, something's wrong with the program, and the operating system knows that and can stop the execution. So here you have the canaries in between the stack frames. To illustrate it a little bit better, here you have random integers. The attacker does not have access to these integers. And so if if they have a buffer overflow from this frame up into this frame, they're going to overwrite that number, and the operating system is going to figure that out. And so that's how stack canaries work. They will exit the system. And then I want to talk about data execution prevention. So this is another mitigation that's come out the last 10 years or so. It marks some region of memory as non-executable. So if a part of memory is never going to have anything in there you should execute, like the heap in most cases, this simply marks it as non-executable. So no matter what's in there, anytime the instruction pointer is pointed into that region, again, the operating system will realize that and throw an exception and exit. This is supported by the hardware level by the NX bit, which is in every modern CPU, and all modern compilers put this in by default. The combination of stack canaries and data execution prevention is making exploiting the stack nowadays very hard. So most of the action now is in the heap. Still possible. There's still rare instances where you can jump over the canary, things like that, but most of the action's in the heap. And that sort of brings us to ASLR, address space layout randomization, another really powerful mitigation. And the idea here is that it shuffles the memory. So you have a deck of cards when you buy them. They're in order by suit and by number. Then you shuffle them, it scrambles it up. To put it in a little more concrete manner, just as we map physical or virtual memory to physical memory, this is another layer of mapping, ASLR to virtual. Much like the OS keeps track of the stack canaries and knows when they've changed, the OS keeps track of this mapping. An attacker can't get to the mapping, so even if they can control the execution pointer, EIP, it's very hard for them to know where to jump it to do what they want. Now, ASLR is not as effective on 32-bit systems. It's much more effective on 64-bit systems. The reason for that is that 32-bit systems have only 4 gig of memory, so there's really not that much memory. The attack that you can run on ASLR is to do a brute force attack, or also called heap spraying, where if you can, you try it again and again and again. You just try jumping, and you try to jump where you want to go. Hopefully, you'll land where you're trying to get to. And so that's one way to defeat ASLR. But in general, it's pretty powerful. OK, so that wraps up the review of memory corruption bugs. We're going to talk about how I go from having those bugs to getting it either determined to be exploitable or not, or to start down the road of finding the root cause analysis. The steps are: you minimize the crash corpus, run memory corruption tools over it to get information about the crash, and then finally determine the exploitability or find the root cause. So typically, especially if something's never been fuzzed before, you can get a lot of crashes, like dozens, pretty common. And so, how do you deal with that? What if you have 50 crashes, 40 crashes? You need to minimize the crash corpus. And by that, I just mean the set of crashes that came out. The first step is to minimize the corpus itself, the number of crashes. And there are tools. AFL has a tool. It's called AFL CMIN, AFL CMIN. And what it does is that it takes the corpus of crashes, and it will run the target again with those crashes, and it will determine if those crashes are actually the same bug, because often they are. AFL and other fuzzers, they do their best to not have duplicate crashes. But for various reasons, during the fuzz run, it's hard to do that completely. And so that's why you need to run a tool like this. This will take you, maybe from a dozen or 2 dozen crashes and get rid of some of the things that are actually the same bug. Hopefully reduce it down to, a minimum number of crashes. The next step is that each of those crashing cases itself must be minimized. And in this case, the fuzzer is just throwing lots of stuff at the target. And a lot of times there's extraneous bytes in the crash case. There almost always is. And so there's lots of stuff in the crash case. Only some part of it is actually responsible for the crash. So crash minimization tools, and AFL's is called TMIN, T-M-I-N. they will take a crashing case and run it over and over again, reducing it, taking out bytes and seeing if the crash still happens. If the crash still happens, that byte is gone. So you can take a file that's, whatever, could be pretty big, could be a kilobyte or whatever, and reduce it down to just those bytes that create the crash. And so that makes it, again, a lot easier to zero in on where the crash happened. There's not extraneous bytes that are doing other things with the program that have nothing to do with the crash itself. And there's one more pretty cool tool called fdupes, and this is available on GitHub. And what fdupes does is that it uses an MD5 hash. And MD5s hash every file in a directory, and it compares those hashes. And if any of the two files are byte to byte identical, it will take one of the two and just delete it. Or it'll flag it, but typically one, just get rid of it. And because even the crash minimization tools aren't perfect. And so I've definitely seen cases where I run the crash minimization, the Corpus minimization, and I still have crash cases which are literally identical byte to byte. So I just like to run fdupes to just get rid of those. So now that we've reduced, minimized the crash corpus, the next step is to dig in and just see what went on. And there's a few tools that are really nice for that. The first thing to say, though, is all bets are off. When things go bad in a C program, when memory gets corrupted, anything can happen. So the tools themselves can have problems. So it pays to be a little skeptical about what any tool tells you what went wrong. Most of them are pretty good, but you don't want to believe everything that comes out of a computer. So the first one is called Address Sanitizer. This is part of GCC and Clang. It operates at both compile time and runtime. So at compile time, it puts in extra instructions to instrument the program. At runtime, it replaces the malloc library with its own runtime allocation library. So again, it can keep track of what's happening at runtime. Those two items in conjunction make ASAN very powerful. It has a lot of information. It had the opportunity to instrument the code at compile time, and then it can watch it very closely when it's running. So it has a high degree of accuracy. I've never seen it report anything erroneous. In some cases, it doesn't tell the whole story, but it is very accurate. It's available in both GCC and Clang, mentioned that, and that's a flag you want to send to it. And it finds invalid reads and writes in both the heap and the stack. It's very good at finding UAFs. It will find double freeze as well and other more minor memory corruption bugs. This is an example of the output of ASAN. You can see it found a UAF. It gives you data about various pointers, as well as where the bad read happened, where the crash happened. This is a stack trace. In this case, we don't have function names due to how it was compiled. But it gives you quite a bit of data about what exactly went on. That's where the bad write happened, and tells you where the crash happened as well too. So ASAN is a very powerful tool. Another similar one is called Valgrind, or I call it Valgrind. Valgrind is actually a family of tools. People kind of use it interchangeably. The actual name is memcheck. Unlike ASAN, memcheck doesn't require a recompile. It can operate on uninstrumented binaries. It does add lots of overhead, slows down the execution quite a bit, but that's hopefully not a problem when you're dealing with crashes. If you have lots and lots of crashes, that can be a problem, but could just take a little while to get through them. It does have a lot of output. It needs to be interpreted. We'll see an example of that in a second. What I like to do is use it with ASAN, because they both give slightly different views on the same crash, and you can really, really understand what went on using the two of them. However, one quick note, you can't use them together. They don't play well together. If you run Valgrind on an instrumented, ASAN instrumented binary, it will complain. It's also pretty accurate. But again, it doesn't always tell the whole story. Sometimes there's more going on. Like what it tells you is true, but there's sometimes can be more going on as well. Here's a quick example of memcheck output. You see here we have invalid write as size 8. A little later, invalid read as size 4. Here we are getting the function names in the stack trace. Compiled this with the proper flags to get that. And so in this case, this is the same crash as the UAF we saw with ASAN. And this is pretty likely to be exploitable. You have a read and a write, and they're close together. So it's likely to be exploitable. If you can get bad data in with control something with a bad write, and then later there's a bad read, you can raise quite a bit of havoc. And then one more tool that's important to run is just called exploitable. It was developed by CERT. It's since been open sourced. So it's on GitHub. Here's the GitHub page. It's actually an extension to GDB, the debugger GDB. It can be run from within GDB, but it doesn't have to be. I usually run it as a script. They supply a script, and so you can simply run this script, give it the crashes, and it'll tell you what's going on. This tool is written in Python. Yeah, you can kind of see the blue. And here's an example of the output of exploitable. And this is the same bug that we're seeing with the other two. And what's nice about this is it gives you a really clear explanation of why it's considered exploitable. That it is exploitable, first of all, it categorizes them. So it categorizes any crash into one of 4 categories. Exploitable, probably exploitable, probably not exploitable. Those are typically null pointer dereferences, and unknown. If exploitable doesn't have enough information, you can detect that something went wrong, but it just can't tell exactly what the problem was. And so it'll say unknown. You kind of got to, in that case, dig into it yourself a little bit more. But these 3 tools will give you a great deal of information and put you in really good position to do the next step. So we've reached the point where we've minimized the corpus. Now we have a lot of information about it. We need to dig in and find out exactly what went wrong, and if it really is exploitable and how. Before we do that, it's easier if you disable ASLR. So after talking about what a great mitigation it is, now I'm saying disable it. As white hats, you have to be careful. You have to, often you run as root too. So run as root and disable ASLR. Great. Do this obviously behind a firewall or a NAT or in some kind of safe way. This is the command on Ubuntu to do this. Randomize_va_space is how you control ASLR, and it's under proc. So as it's under proc, you cannot use VI or any other editor. You have to echo a 0 into it to disable it. If you disable it this way, it won't survive a reboot. And yeah, I want to reiterate, do it carefully. Once you've done that, I think it pays to even write down exactly what the critical memory locations were for that crash. And there can be 2 kinds of memory locations that you care about. Instructions, code, locations of that, and data itself. And it's easy to kind of, once you dig into these things, it can get confusing. So I have to be pretty careful about keeping track of if the location is a data location or a code location. So some examples are certainly where the crash happened. That's a code location. That's, these tools all give you that. That's the place to start. That's a very important memory location. Certainly where the invalid read and or writes have occurred as a data location. If it's in the heap where the memory was allocated, where it was freed, that's a code location. And also if the data has been reassigned during the course of the program, if the variable has been reassigned to another one or copied, things like that, you've got to track the data through the flow from the input to where it actually crashed. And that's actually could be code or data location. And then once you do that, you kind of just have to dig into it. Use the GDB debuggers is where I spend most of my time. And typically the best approach is just to set a breakpoint where the crash happened and then work back from there and figure out how it reached that point. Now you saw how I used lots of capital A's on some earlier slides. And I'd like to do that. It's a very common thing when you're doing crash triage, is to send it a bunch of capital A's, and then those are very easy to see when you're dumping memory in GDB. So the idea is that you can track the memory kind of keep track of it. If you see a bunch of triple A's or capital A's, or in memory, what you're going to be seeing is the number, hex number 41, because that's the ASCII number of a capital A. And so the game is, and it's not easy, you just kind of have to set the breakpoint, send it different values, larger, smaller, figure out what went wrong, understand you have those other important code points where things were allocated or freed or not. And there's a lot of just dumping the memory. We'll see an example of that a little later, how that works in GDB, but you have to spend a lot of time digging through and just looking at memory, figuring out what's going on. It's not easy. It can be fun, I like it. Not everybody does. One thing though that can make it much easier is a very cool tool called RR. RR is itself a GDB plugin, like Exploitable was. RR is a project by the Mozilla Foundation, and it's a very cool open source tool. The way you use it is you run the executable, the target executable with the crashing case, and you record the execution of that. RR takes care of that for you. So while it does that, it gathers a lot of information about it to the point where you can then debug in reverse. So normal debugger, we set a breakpoint and we do step into, step next, step over, step out of, but it's always going downstream. You know, time is always moving. It's always moving along the time arrow from when you started execution of the application to where it crashed. RR is very powerful because it lets you do the opposite. You can set the breakpoint at the crash and step backwards, next backwards, all that kind of thing. So it makes it far easier in many cases to find the root cause, because you're just going backwards and you're seeing what is happening in reverse up to the point where maybe the bad free happened or whatever the problem was. So without this, with GDB, I find myself just running things many, many times and just setting breakpoints kind of sooner and sooner and sooner in the the control flow execution of the application. But that can be very time consuming. So RR is a great tool that can really help things out with that. One quick caveat about RR is that you cannot alter variables like you can in GDB. Like you can assign a variable a different value. Or in GDB, you can make a call from the GDB command line. You can just call some function, and if it's memory, it will run. If you do either of those things, it's going to crash RR because you've changed reality. Like RR records what happens. Once you start messing with that, RR doesn't do well. Typically, both RR and GDB will crash if you try that. And so those are some very cool tools to dig into this stuff, but it's not easy. This can take a lot of time, a lot of practice, and it can be frustrating. So persistence is key, and really just do your best. And then one final thing to talk in terms of fuzz runs and managing this part of things. Many crashes actually can mask another crash down the control flow. So program exits at a given crash, great, you're working on that crash. The idea is you fix that crash, and then you must fuzz it again, or you fix any crashes you have. You definitely need to refuzz the app one more time, probably several more times, to make sure that the crashes you found are not masking more crashes or other memory corruption errors down the execution of the program. Okay, so I'd like to wrap this talk up today and show you a couple of real-world examples from my own research. The first one is pretty trivial. It was in PHP. It's a low invalid read. Here's my report to it. I was fuzzing a PHP ini file, and I was doing that from the command line, which is a little strange because PHP ini is typically when you're running PHP in the context of a web server. And it's also not necessarily a great way to find exploits because the PHP file is controlled by the admin. And so it's hard to see a bad guy getting a PHP ini file with crafted malicious data in it to run. And so unless the admin has been compromised or the admin is malicious, it's not a great approach, although it can be. We'll see another one in a second. This was not. We have here a low read. Here's the crafted ini file. This is the line that the fuzzer came up with, and I was using a dictionary. So the fuzzer was just using these known values. And the fuzzer threw a 1 in here, and it thought it was running in a web server, and it wasn't. It was running from the command line, and it shook out this crash. But it's completely not exploitable. Here's the memcheck output. It's a bad read of size 4, but it's very, very low, right? And so this is a null pointer dereference. We're at address hex 10, which is 16 in decimal. And Valgrind said this address is not stacked, malactor free, and so it crashed on this. But a very low bad read. There's never anything down there in memory. There's never anything of use in a process at this memory address here. And here's the fix that the PHP maintainers put in. You can see they just added a line to check if it's running as a server or not, and then do the appropriate thing. So then I turned my attention to Ruby and decided to fuzz the regular expression mechanism in Ruby. Now this is a compilation of the regular expressions that programmers write. And that's distinct from when compiled regular expression actually handles input data and applies itself to that. That I didn't fuzz. This is just the regular expression itself. So I fuzzed Ruby with lots of weird regular expressions, and I was able to shake out heap buffer overflow. And here's the ASAN output from it. And so ASAN, very clearly called it a heap buffer overflow or a bad read of size 4. I ran Valgrind on it, and Valgrind also found a bad write of size 4 as well. And you can see these memory locations are, again, fairly close together. And so this looks pretty exploitable, and it probably was. There's one caveat to that, is that it's rare that an attacker can supply a regular expression. So usually attackers supply data which has an existing regular expression applied to it. There may be some cases where some app somewhere allows you to upload arbitrary regular expressions, but they're rare. So while this is highly likely to be exploitable, the attack surface arguably is very small. I mean, it's really hard to see how somebody's going to exploit this in the wild. So I reported it, and they did a nice fix here. It turned out that if you have a character class in a regular expression, you open it, and then you don't close it, and then you also have an octal number in it, that weird case, that weird corner case, is what triggers this button. And then one more. The last one is in an open source system called Netflix Dynomite. Netflix Dynomite is a tool that runs between the open internet and Redis and memcached key value storage systems. It's an open source tool that Netflix wrote. It's on GitHub. And here's Netflix is saying that they run this real. They run this in production. I believe they run it to store metadata associated with people watching movies. They're obviously running at scale, and other people are running it too. It's pretty popular. And so again, I fuzzed the, in this case, the YAML file. So it has dynomite.yaml. That's how you configure Netflix Dynomite. And so I decided to fuzz that. Again, a weird, it's an oblique attack. And I figured most people, it's probably been fuzzed head on before. People probably fuzzed it with what comes over the internet. Maybe not, I'm not sure. But I try to attack obliquely at first on things that I think have already been heavily audited. So I did that, and I got a crash. And I also thought, well, okay, it's probably going to be in the YAML library because it's parsing the YAML, and they were using some other library, and so maybe I'll get a vuln in that, or maybe not. So I went for it anyway, and I got a pretty nice crash. And so here's what the input looked like, and you can see we have some A's in there. This is actually just been reduced and carefully crafted, and this here is the output of glibc. So when things go bad, glibc will also give you information about this. This comes out of standard error. And this is within the context of a GDB session. So I started this in GDB, ran the program. The -t just tells it to read the YAML file, I think. And we got a crash, and I dumped the data from GDB. X means examine. This X means show it as hex. And this is the memory location I was interested in. And you can see we got a set of 41s here. So my attack payload did make it through into memory. I was able to successfully write that. So I could have written anything I wanted. This is also a 6-byte overwrite. We've got 2 more bytes here. And it is contiguous. This is Intel, so it's little endian. So you need to reverse this memory location. So it actually was 6 contiguous bytes of code there. And so I reported this, and I was like, okay, whatever. I wasn't sure where the problem was, and it was obviously a serious bug, and in time to report, worth reporting. So I did, and then this is their report here, and it turns out that this was down in the string function. So I was pretty shocked when I saw this. They got the actual bug that they fixed was down in their string dupe code. And so rather than this just being a bug that a bad admin could leverage through a crafted YAML file, this looks like a far serious bug. Now, I haven't tried this. I haven't tried to exploit it. I haven't fuzzed it head on. I reported this. It's been fixed for about 7 months. And so I was really surprised, though. I was like, wow, actually pleasantly surprised, because I'm like, wow, this is a pretty bad bug. And so I believe this could have been pretty bad for Netflix. If you could leverage this, you essentially have man in the middle between the internet and their key value stores. And so this is their fix, and this is the diff of the fix. And they have a string library, but they weren't fully using it. They were kind of doing their own coding over it. And that's where they got into trouble. And you can see, again, this is a classic off by 1 style error. Another fix down here as well. And so that was a really good bug, and I did report that. I did get in the Netflix Hall of Fame for that. They don't pay, but it's a highly sought after place to be, and I've got some good company there. And then finally, I want to talk about a few really awesome references that helped me learn all this stuff. Rensselaer Polytechnic Institute has a course called Modern Binary Exploitation. Now, they've very generously put all the course materials online. There's on GitHub, there's open source vulnerable apps to practice against, and also all the PDFs and slides and everything else are also part of what they offer. So I went through the whole course, and I learned a lot. And it's not just exploitation; they cover reverse engineering quite a bit too. It's a great course. The next one, Hacking the Art of Exploitation. This is pretty much the book, the Bible of this kind of work. I bought a copy in 2005. The 2nd edition has come out since. It's a great book. Highly recommend that. And then a couple of these blog posts, very interesting as well. Highly recommend those. And that's going to do it. Really, thank you guys very much. Thank you so much for your attention. Really appreciate being here. Any questions? Any questions about this stuff?
I got a question.
Yeah.
So one thing that you touched on earlier at a high level was just how many libraries go into applications nowadays. Mm-hmm. And so that's the challenge that a lot of my customers face. They say, hey, we're shipping a product, but underneath the hood, we have like 50 open source libraries.
Yes.
So, at a high level, is there any products or solutions or recommendations you would give me to say, hey, this is something that you might want to check your code against, both static or dynamic analysis?
Yeah, absolutely. So the question was, if you're using lots of other libraries, we all ship code with other libraries in it, and how do we know what's going on in those libraries? And the question sort of follow up is like, is there dynamic analysis? And there are companies that are doing that in some cases, handling that. And you're talking about another really important use case, right, which is third-party code. And that's another thing that's very worthy to fuzz if you have time, or one way or another. I mean, it's important to fuzz that stuff or run static analysis tools over it as well. And so, so absolutely, there are companies that are doing that. There are some that are doing static analysis on JavaScript libraries, like in Node, because there's so many of those. And there are certainly, there's obviously pen test companies, they'll fuzz stuff for you. And there are a couple of companies now that are doing dynamic analysis fuzzing in the cloud as well, that you do it, but those companies will supply the infrastructure, right? And so you don't have to have your own computers and all that kind of stuff. You just send them a binary, they'll do the fuzz run, and then come back some of them actually give you all this data that I showed you. And so, does that answer your question?
Yeah, just like, like application security is tough.
Yeah.
And a lot of my customers don't do it well.
Yeah,
and so
or do it at all.
They ship buggy products, basically,
Yeah.
right? Because
Yeah.
the SSL version that they're using in open source is outdated, and then you get a whole bunch of problems.
Right.
So I was just curious if there's like a solution or a vendor that you know of that can do that kind of thing.
Yeah, there's no one single thing. It's
Okay.
really, yeah, unfortunately there's not at this point. You still have to kind of do it by hand, or I mean, although I mean it's an interesting field, and I'm sure there's probably, I mean, that might be a good startup. Okay. Yes.
How long does it typically take? Say one of your examples. I mean, you spend a half a day, 2 days, a week.
It varies quite a bit, but I would say probably at least half a day on any given crash, and that's kind of in the good case. But the question was, how long does it take to manage a crash once you have it? Does it take me half a day or a day or whatever? Ideally, it doesn't take that long, especially so many of these off by one errors are easy to track down. Like it's easy to figure out a off by one error. If it's not that, it can be who knows what. And I'm getting better at it too. So, and then if you're including writing the report, you're obviously looking at a couple more hours for that. And so it probably takes about a half a day on average to a day for any given crash to really fully investigate it, to get to the point where you'll be able to tell if it's exploitable or not, or have a good shot at finding the root cause. Anything else? Yes, sir.
Do you ever fuzz like .NET or Java applications that are at runtime? Is there much fruitful findings in those applications?
Yeah, that's a great question. So the question was, have I ever fuzzed Java or .NET managed apps, right? Yes. So we're talking about here memory corruption in unmanaged C and C++ code. That's what my whole talk has been about. The question is, what about Java? What about .NET or any other managed system, right? And I'm actually really interested in doing that. And I think there is, I think there's a lot of study and research that can be done there. And I'm very interested in finding that. Or I sort of call that fuzzing for correctness, or fuzzing for conditions other than crashes. So, fuzzer, generally it throws random data at a program, and it monitors it for some condition that matters. Almost always these days it's a crash. And crashes are easy to see, right? But you could certainly fuzz for other conditions. And so you'd have to predefine those conditions somehow, and that might take a lot of work. I'd like to think there's some automated way to think of those conditions, or maybe based on the test suite. And one other similar thing that I'm looking at is called differential testing. In that case, you fuzz three programs that are different, but they perform the same function. Like there's multiple Ruby interpreters. So you could fuzz 3 of them at the same time, sending all 3 of them the same crafted or mutated case. And then you compare the output of them. And certainly if 2 of them have one answer, and the other has a different answer, you potentially uncovered a bug in either one of them or 2 of them. And so that's another thing that I'm really interested in as well. And so yeah, I mean, I think that there's a lot of room for fuzzers to find more bugs in more kinds of code. And there's other research, it's pretty active research in some academic communities on that as well. Yeah, thank you. Anything else? All right, thank you guys so much.